Alright, so we've got a revision seminar for Eng Maths IIB, which I wasn't going to do. I'm going to leave you all to your own devices, but then I went, I'll stuff it. I'll give it a go. And we'll see how it turns out. Since when I emailed Barry asking when his consulting time was, he said, oh, it's the same as it always is, from 1 till 2 on Wednesday, and I emailed him at like 11 o'clock on Wednesday. So it was a little bit too late to do anything about it by then. And happens to be the same as the consulting time for Maths 1B, which he's also teaching, so he doesn't really expect anyone to come. So I decided I would do something. Yes, I would do something. And since someone asked me at some point last week, could you say something about the integral bit, I thought I'd give it a go. So be aware, it's been a very, very long time since I've studied this myself, and it may have been never for some of the bits of this for studying it myself. So I'm going completely on what is in your notes, which is supposedly the best thing to do, right? If it's in the notes, it must be true, and it must be something that he wants you to know. So I'm going to talk about how I understand this. So the vector calculus bit was mostly in 3D, and most of the examples I found that were in 2D were in 3D anyway, because he just tacked on a 0 for the third coordinate. So it's all in 3D space. And there's these ideas of functions that either take vectors and produce vectors, or they take vectors and produce numbers, or they take numbers and produce vectors. And those produce different shapes in space. So the two big ideas were what he called a scalar field and a vector field. So the concept was that is not a V. We've got x, y, z coordinates, and the way a scalar field works is that every point in space is given a number. Okay, so there's some formula that if I take the coordinates of some point in space, it will produce a number. And so this point will have a number, and 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 every point in space is assigned a number to go with it. Okay? Now we're used to thinking of functions as something that has a domain and a range, and you can draw a graph of it, but we can't because the points that we're using are in 3D and we don't have a fourth dimension on which to draw the result. So when they saw it as a scalar field, they're talking about saying that there is points in space and every point is assigned a number. Something like the temperature in the air in this room. Every point in the air has its own temperature, and you could have a number at every point. And the idea is that you can pick a point anywhere and zoom in on it and look closely, and it will tell you a number that says what the scalar field is at that point. Okay? That's a scalar field. Lovely. And one of the things that you do with a scalar field is you find all the points that produce the same outcome. So if you get all the points that have the same number, give me a second to find my picture. If you get all the points that have the same number, what you'll make is some sort of surface. So, that's really bad, sorry. This doesn't pick up colour very well. So this might be where the scalar field comes out to 7. This might be where it comes out to 6, this might be where it comes out to 5. And everywhere in space you can say, well, let's find all the ones that come out to 5, and it will produce some sort of surface in space. And you can imagine colouring in every point a colour to correspond to the number it has. The high colours, high numbers are red, and the low numbers are blue, and you'll be able to colour everything in space. And if you pick all the points with the same colour, you'll produce a surface. So here's a surface. the idea is that what I can do is I can take space and every point has a number of its own, and so let's find all the points where the number comes out to 0, and here it is. And there might be all the points where the number comes out to something else might be here, and all the points where the number comes out to something else might be here. And so you just particularly pick out particular spots that come out to a certain answer, and that's how you make a surface. That's one way of making a surface. So in my head, the scalar field is actually made out of a whole lot of stacked surfaces that are all stacked on top of each other, and each one corresponds to a different outcome in the scalar field. Right, that's the picture that's in my head when I look at that. Right, so there's all this stuff that goes on with scalar fields, and you need to do integrals and whatever, and I'll get to that in a minute. The other thing that you can have is a vector field. A vector field is pretty much the same, except instead of every point being given a number, every point has a vector. So what you do is at every point in space, you get that point and use its coordinates to create a vector which corresponds to some sort of direction from that point. Okay, and so here there's some sort of, I might do it in a different colour, it's not red. At this point, there's some sort of vector that maybe points that way. And at this point, there's some sort of vector and maybe it points this way. And at this point, there's some sort of vector and maybe it points that way. And so at every point in space, there is a vector. Technically, the vector's not there in space. It lives somewhere else. It just says that if you go to that point and you sub in the coordinates, what it will produce is an arrow in space somewhere. So it's almost as if at every point, you go to that point and then you produce a new 3D space and draw an arrow there. And go, that's the arrow that belongs to this point. Okay? That's the idea of a vector field. So no matter which point you pick, there'll be an arrow that tells you what direction the vector field is facing. And the classic example from physics is like a magnetic field, for example, hence the name field. So at every point, there's a certain amount of force pushing on you from the magnet, and you can't see it, but you can feel it. So it's almost as if every point here has a feeling, and this arrow describes what its feelings are. Okay, I feel that I should go that way, and that's the vector field, corresponding with David's normal way of interpreting most maths in terms of personality. So, yes, that's the picture that you have. Now, the problem with your vector field, your scalar field has this lovely representation of a whole lot of stacked surfaces. The surfaces might be balls, they might be inside each other. This one's not so easy, and I can't think of a good one for that. But what you can do with your vector field is that you can turn it into a scalar field by doing some sort of dot product with something or other, and that will produce a scalar field. You could, for example, find the length of all of those vectors, and then suddenly what you'd have is a number for every point. Okay, so you can turn a vector field into a scalar field if you want. You can also turn a scalar field into a vector field if you want, if you think carefully about it. Okay, so, right. So the way to turn a vector field into a scalar field is to dot product all of those vectors with something. And then what you'll produce at every point, you'll produce a number. Okay? And that's the big idea for integrals. Every integral of a vector field is actually the integral of a scalar field. That's the dot product of your vector field with something. Okay? And you can go from a scalar field to a vector field by finding normal vectors to those surfaces. So if your scalar field is made up of those level surfaces, they're called, they're all stacked on top of each other, at any point you can find your, at this point here, you can find the normal to the surface that it lives in, and suddenly now every point has a vector associated with it, and you can produce a vector field. So, and this idea that I can get from a vector field to a scalar field by doing some sort of dot product and I can get from a scalar field to a vector field by finding normals to the level surface, is the whole idea that all those Green's theorems and Stokes theorems are based on. So reading through it, that's what I got from it. That's the picture that's in my head. Okay, and then we need methods of picking the right thing to dot those vectors with. We need methods of finding those normal vectors, and we need a definition of what it even means to say an integral. But we have a couple more things that we need to know about, which is how do you know, I've produced that surface there from a scalar field. There's another way to produce a surface, and there is also ways to produce paths in space as well. So we also have a path. And in my head, the concept of a path is that you have some sort of line somewhere which is not in space, it's just somewhere else, you keep it in another room, and it goes from some point to some other point, and it's usually the t-axis. And you use all of these t's and you sub them into a formula to produce something in space. And that's your path or curve. Okay, so this is a parameterization of the curve, and you have some sort of formula that takes that gives you an x-coordinate, a y-coordinate, and a z-coordinate, all based on t. So you have an x based on t, a y based on t, and a z based on t. Right, and I'm going to do a 3D picture of that. Oh, that's not what I expected to happen. Zoom in a bit. Okay. That is my path in space. Okay? Somewhere there is a line. It's not in space. Somewhere there's a line that has my t's on it. That's upside down for you guys, isn't it? Somewhere there's a line that has my t on it. And as you trace along the t, it moves the point along your surface, along your path. That's what a curve in space is. Okay, every one of these points t corresponds to one of the points on the surface. That one is there, that one is there, and then all the points in between that correspond to one of the points on the surface. Yep. I think it can, but we normally ignore that because I think it causes problems with the integrals. So your lecturer defined different types of curves. So there's simple ones that don't double back on themselves, and there's closed ones that come back to where they started. So you might have a curve that does that, which comes back to the place it started. That's okay. That's called a closed curve. And then one that crosses itself is called non-simple. And so in this course you only look at simple and simple closed curves. Okay, so one thing I need to point out is that this length here is not always the same as this length here. Okay, so I get my curve and I flatten it out. It might be quite a bit longer than the length on the t-axis. If you choose the length on the t-axis to be the same as the length of your curve, that's called parameterizing by arc length. But it doesn't have to be the same. So there's always some sort of chain rule thing going on where you can say that a small change in t has to correspond to a much bigger change on the actual surface itself. Okay? So this small change here is a really big change here. And that's really important for doing integrals. Okay, my curve is getting wonkier and wonkier. Right. I will draw a diagram of it because you can't take a big foam square and pieces of wire into the exam. I'm sure you could, but I'm not sure. It'd be like taking scissors onto a plane, right? Okay, so the concept that I just mentioned was that a distance here, which is a dt, might correspond to quite a long distance here, which is your ds, where s is arc length along the thing. Okay? And that's the idea of a curve. That's what a path or a curve is. It can cross itself because there was one in the assignment for the complex numbers that went looped twice around some things, so it is okay to do that, I think. Okay. Cool. And then, of course, there is also the concept of a surface. Now, not a level surface, but just a surface, which is similar but two-dimensional. So with a surface, instead of having just a t, there's like an s and a t, or a u and a v, which is what he normally talks about in the lectures. And so what happens is that you get some zone here and the process that does that is the same, except it's like x of uv, y of uv, z of uv. And that function takes these things and produces things over here. So a point somewhere there might end up over here on my surface. Right. So we have two ways to make surfaces now. We have to make, so these is parameterizations here. We have ways of making surfaces by saying I'm going to pick two numbers, a u and a v, and each u and v is going to tell me one of the points on the surface is actually in space, but the u and v live somewhere else. Sometimes you can actually draw them somewhere on these x, y, and z axes, but sometimes they don't live there at all. They're just somewhere else. And the other way of making a surface was to do a level curve for a scalar field. Okay? Right. So they're the pictures that are in my head when I'm thinking about these things. And you can combine these things as well because you can make paths that are inside surfaces. He did mention it a lot, but that's how the proofs work of a lot of the things. But he didn't ever ask you to do any of that as far as I can tell. So, yes. So, I think I'm doing okay. So they're the pictures in my head of what's going on. And now I'm going to just run through what I've found in the notes about integrals. And the first type of integral was a path integral in a scalar field. Okay, so what we're going to do is we're going to combine this picture with this picture. We're going to draw a path across a scalar field. Okay, so we have a path and it's in 3D space, and the 3D space, every point in 3D space has a number associated with it, and that is what we mean by a scalar field. So we're going to combine those pictures. Path in a scalar field. So I had every point had a number, and if I pick any one particular number, I can draw a level surface. And then my path runs through space like that. Now this is the bit where I find the surfaces particularly helpful. When this path crosses one of the surfaces, the point on there has the number that belongs to that surface. So I had like 5, 6, and 7 on my diagram here. Obviously, there has to be one in between where it's 5.5 and one in between where it's 5.1 because it's all continuous. But my path will cross my surfaces various numbers of times. Okay? And when it crosses this surface, the value of the number at that point on the path is 5. And when it crosses this, it's 6, and then it's 6 again, and then it's 7. And everywhere in between, it does whatever it does. So what I want to do is I want to take those numbers and add them all up. So I'm going to hopefully make my 3D drawing work. I'm just going to need a strip of paper. In fact, I might just use newspaper so it's long enough and flexible enough. The advertisers started sending us papers every day because we get the paper from them on the weekend and they want us to buy it every day for free for a couple of weeks. So I have this surplus of newspaper, which is most useful. Okay. So, idea is every point on this curve has a value for that scalar field. Maybe here it's 6, and here it's 7, and here it's 8, and here it's 6 again, and whatever. Okay? And so what I need to do is I need to somehow figure out how to add up all of those values across the curve. Now we're used to doing that with numbers because we can just draw the graph and add up the area, and we do all these vertical slices, but there's no direction to draw vertical in this sense. So what I'm actually doing is I'm taking this and I'm stretching it flat and going, well, at this point it was 5, at this point it was 6, at this point it was 7, and what I'm making is this long strip along here that I need to add up the area of. Okay, and I'm supposed to do it literally on the curve itself, so that distances along here, down there represent arc lengths. But my problem is that the only way I have of describing the curve is here, from 0 to 1 or whatever on my t-axis. So somehow I have to squash this onto the t-axis. And in order for it to be the same area, I have to make it taller. So what I'm really doing is substitution. Okay? Some sort of substitution like way back in Maths 1A. So I need to have the right area even though the length on the t-axis is not the same as the length here. Right? That's the reason why you have to go through all this effort. But the formula for it, that's the reason why the formula is the way it is. But what you do is this. Let me just see if I can just find the formula. So we define that the integral across the curve C of my function f, because remember my function f is the scalar field, okay? F for function, F for field. And that f tells me at every point what the number is, and that f tells me that all of these points on this surface have the same number, okay? So that there, right? So the picture is that we have, I've flattened out my curve. And at some point it's 5, and at some point it's 6, and then it's 6 again, and then it's 7, and I can draw the heights representing the value of the scalar field. So this height here is the f. Okay? But my problem is that I made my curve by doing a t-axis. Where's my original picture go? Yeah. I made my curve, this is the s-axis here, but I made my curve by doing a t-axis, so I need some other way of figuring out this area so it works out right. Okay, that's what's in my head. Okay, so the picture, the way it works is you're going to use your t. You're going to get your f, which is a number. And you're going to multiply it by the length of the derivative of your points on the curve. So the idea is that every point on this curve can be represented by a vector which we call x, and that x has coordinates which are involved in t, and you can differentiate each coordinate separately and find the length of that, and then you go from t equals a to t equals b. And that's what I found in the notes. That's the length, yeah. And that's how to integrate a vector field across a curve. So, as an example, scalar field. You know, we're just a random curve. Oh, that's a vector field. So the curve has to be made out of t's. Something like that. Got t squared 0 just to make it simple. For t between, I don't know, 0 and 3. Okay? And I've got a scalar field something like that. Okay? So remember, your scalar field takes points in 3D, x, y, z, and gives them a number, and this is the number it gives them. It says my scalar field adds the x coordinate, 3 of the y coordinate, and times the x and the z together and subtracts that off, and that's the number that it gives every point in space. This is my way of making the curve in space, and it's actually looks like a parabola on the xy plane by the look of it. So just as a picture, you don't necessarily need to know how to do this, but there's my curve over here, like that. And every one of those points has a number, and I want to add up all those numbers. So, according to the rules, that'll be from 0 to 3. F is actually, give me some space, but this is what it is. It's going to be f times the length of x dash squared dt. So I just need to figure out what all those things are. So let's see. F was x plus 3y minus xz, but I have to use the points x that are on my curve, because technically this is my vector x. So I have to use the x coordinate is t, the y coordinate is t squared, the x coordinate is t, and the z coordinate is 0. So that's my f in terms of t. I've converted it to be in terms of t. My x dashed, well, let's see, I just differentiate each term of that. So the derivative of t is 1, the derivative of t squared is 2t, the derivative of 0 is 0. And I need the length of that. So that's root. I've made this hard for myself, but that's okay. And so therefore the integral of c of f ds is actually from 0 to 3 of f, which was t plus 3t squared, and the length of x dashed and I do not like my chances of figuring that out today. Okay, but now this is back to something that we could hopefully have done at some point in Maths 1A and or B, and figure out that integral, which looks horrifyingly like I should use some sort of trig substitution, but I won't. Okay, so one of the reasons why in exams they use straight line paths is because it produces pleasant properties for the length. So if you use a straight line path, then your derivative here won't have any t's in it, and so the length will just come out as a number, and so it'll be easier to do. Okay. All right, but that's the definition of a path integral across a scalar field. So what about a path integral across a vector field? So my picture is I have a vector field. Every point in space has a vector to go with it. That's great. And then somewhere in space there is a path running through this vector field. And your path has been made by using your t-axis from A to B. Okay? Now that's not so easy, but as I said, the only way to do this is to turn your vector field into scalars. Okay? So one way of doing it would be to use as the scalars the length of each of those vectors at any given spot. So at this spot there is a vector and it has a length, and at this spot there is a vector and it has a length, and at this spot there is a vector and it has a length. What we're actually going to do is we're going to find out what length the vector field is in the direction that the curve is facing at this exact moment. So let's just zoom in on a little bit of my curve. All right. There's a little bit of my curve, and here is a point on my curve. Now the vector field itself, which I should have chosen a different colour than red, the vector field itself, maybe it's facing this way. Right, that's my vector field, which is underlined because it's a vector. It's a bold F. And my curve has a tangent just there, and what I want to know is how much of that F is in the direction of this tangent. So I want to know what this bit here is. That bit there. If I can find the length of that vector, then that is what the length of that vector is going to be my new scalar field that I'm going to integrate. So I want the length of that. And the length of that is a dot product. To find how much of a vector points in the direction of another vector, you should do a dot product, because that's what dot products do. And if the tangent vector that I dot it with is a unit vector, it will come out to the correct length. Okay? So what this will mean is that it will be f dot with a tangent vector that's a unit vector, and that will be the length that I'm going to integrate. Okay? So the upshot of it all is that the formula comes out to this. Okay, formula comes out to the integral across my curve C of a vector f dot with dx. So it's all vectors now, so we do it as a dot product, is the same as a scalar integral, which goes like this. F dot x dashed dt. Okay, so that f is the vector at this exact spot. At any particular spot on the curve, it's the vector from the vector field, and this x dashed is the vector that points in the direction of the tangent. Okay, so this is my vector field. And this is the tangent. But in the end, what I've really done is I've turned it into a scalar thing. So technically what I've done is I've actually dotted it with a unit vector in this direction, so I've actually divided it by the length of x double dashed. But if I was going to do that scalar, I would have to times by the length of x double dashed too. So it works out like this. And this is actually much easier than a path integral. So as an example, I'll use the same curve. Was it 0 to 3 that I used? and then I've got my f this time is a vector something like that, just a random one off the top of my head. Okay, and in order to figure out the integral, I need to know various things. So that's my x there. So let's see. To find the integral, I need to know what f is in terms of t. So f t. It's a t there. So x is t, x is t, y is t squared, z is 0, y is t squared, so I just sub that all in. That's my f of t. I need to know my x dashed. So I differentiate the x. Derivative of t is 1, derivative of t squared is 2t, derivative of 0 is 0. And I need to know what their dot product is. And that comes out to t plus 2t to the 4 plus 0. And so therefore, the integral of my f across the curve dot dx is actually the integral, I might just change that c to the ab, right, is the integral from 0 to 3 of t plus 2t to the 4 dt. Which I can actually do, right, because it's much easier than the last one. So. And I'll sub it all in, it'll give me an answer. So that's path integral. So it took me a while to get a handle on that, but that's what we've got. Now before I move on to anything else, there's something that I said there that came up that was sort of interesting. Which was that x dashed was the direction that the tangent points. You might remember one of the assignments he said, oh, here's two curves, show that they intersect at right angles at this spot. That means that you should find the two tangents and dot product them and see if they come out to 0, and then they would come at right angles. So just worth pointing out that on a curve, I might go and add this back here on the curve. On your path curve, x dashed points in the direction of the tangent. So, useful piece of information that he brought up in an assignment. So, yeah, okay. I will put these on the Maths Learning Centre's webpage under Eng Maths IIB, so you can use them. So that's paths, which was lovely. And the other things were surface integrals, which is where it starts to get a little bit trickier. How are we feeling? You're all good with this so far? Because I only learned this morning, so you've got to give me a chance to run through it in my head. So the next thing is that we have surfaces, and instead of having a path in my scalar field, I have a surface in my scalar field, and instead of having a path in my vector field, I have a surface in my vector field, and instead of adding up the number across the path, I add up the number across the entire surface. So it makes some sort of volume, okay? And so you need methods for thinking of how to do an integral in two directions at once. But first we'll just define some stuff. So give me a second. Right. So we've got a surface in our scalar field. Every point's got a number. And you have a surface living in this scalar field somewhere, which I will colour in red. And your aim is to try and add up all those numbers that are at every point for all of the points on the whole surface, and that's what your integral is. And so you have this I think that's how it's written, possibly with a ds, so something like that. So the concept that you've got there is that at every point on the surface there's a little block of a little square, and on that square you sort of say, well, the average the average number on that is this number, and then I'll just add up all those numbers across all the little squares and make the squares smaller and smaller and smaller. Okay, and then what it says is that you'll begin to imagine that you had a region over here that produced your surface. That's your region R, and it, through the parameterization, produced the surface. So this was the U and this was the V, and you'll get that's what it says in the notes. That is a bold N in those absolute value signs there. So that N is the length of the normal vector of your surface at that point. So every point on the surface has a normal vector pointing in some direction. And it could be up or down, and you have to choose. And the length of that vector, you're going to multiply it by the f, and that's how much, pardon me, that's how much the value of f is going to count at that spot. Okay, so this is still another of those concepts of the surface might be quite a lot bigger than the r that you use to make it, and so if you use just f du dv, the volume would be too small, and so you have to stretch it out by how big your surface is, which is what that normal vector is about. So, yes. And there are at least two ways to find that normal vector, but the one that I found in the notes is that the points on your surface would be like x. So, finding n. X are the points on your surface, and they're functions of u and v, and you go sort of dx on du, that's a vector, which he calls x sub u, so you differentiate it with respect to u, and you get x sub v as well, and then you cross product them, and that is your normal vector. So that's if you've got it as a parameterized thing. It ought to work that you can do the gradient vector, which I haven't talked about, but it ought to work that you can do the gradient vector of that as a, pretend that that's the level surface of something, and do the gradient vector of the scalar field, and that ought to work too, but it doesn't seem to give you the right answer, so we won't do that. I don't know why, so I'm still not sure how that works. So I'm going to run with this one because that's what he did in his example in the notes. So, yeah. Okay, so that's the rules of finding integrals across surfaces of scalar fields. And what this is going to require us to do, you'll notice that f and the length of n are both numbers, and you can rewrite them to all be in terms of u and v. And so now we just have this expression involving u and v, which is just a plain number, it's not a vector, and we have to integrate it across our region, and you're supposed to integrate the u first and then the v, or vice versa, depending on which way around seems easier. So you have to somehow get this region and choose the limits that go on these integrations. And that's the bit that at least one person has said they find tricky. And I have to say, they have to do this in second year statistics in the maths degree. They have to do this over in economics, and everyone finds it confusing. So don't feel bad, but you still have to know how to do it. So you need to find n, and you also need to be able to find the limits of that integration. And this is going to come out again even if you do an integral of a vector field, because in the end it's going to come back to this same idea again, because you're going to turn your vector field into a scalar field and do that instead. So the way that I always thought about it was that you slice your region into slices, and that's what Barry did in one of the lectures. So I'll just do an example of that bit. So we'll also have to find so we also have to find the limits of integration. Once we've got this, it'll just be a formula of some sort, and we'll have a description of the region. So I'm just going to do an example of doing that bit. Okay, so you might have, it might, for some random thing, come out to have something like that. All right. Oh, that's totally a Jacobian, isn't it? Huh, there you go. Okay, so, and your region is maybe this. Let me draw that triangle there. It's 2 on the u-axis and 3 on the v-axis. So you need to slice that into slices. So I'll draw it bigger so that we can think about it. So you have a choice. You can either do it as horizontal slices or as vertical slices. And it's similar to the process where I would draw vertical lines to try and do solids of revolution back in Maths 1B. So I'm just, for argument's sake, I'm going to pick a vertical slice. And that's a u coordinate there. So what we're going to do is we're going to imagine that that u coordinate ranges from, goes wherever it goes. And so to produce that vertical line, the u will go from 0 to 2. That's the places that the u can be. So I have that u is from 0 to 2. They're all the options for what u could be. And once you've chosen the u and you have that lovely vertical line, we need to know what these are in terms of u, because that's the zone that v can move along. V moves up and down this red line. So I've got that v, whatever this is here, v from whatever a is to 3. But I don't know what a is yet, but that's what it is. So I just need to figure out what that is in terms of the u that I'm up to. So I should probably figure out the formula for that line. So let's see, the line has slope, rise is 3 over run is 2, yep. And so it has equation y equals 3 on 2, v equals 3 on 2u. All right, and so therefore this height here is 3 on 2u because it's on the line. point A has v coordinate v equals 3 on 2u. So what I have is that actually v from 3 on 2u to 3. So my integral is going to be, now let's see, I did u first, that means it's actually on the outside. So the one that doesn't involve any variables, that has to go on the furthest outside level. So I'm actually going to do dv du here. So I've chosen this to be on the outside because it doesn't have any variables in its integral limits. They're just plain numbers from 0 to 2. So the idea is that we choose the u to be from 0 to 2, and once we've chosen the u, we choose the v to be from 3 on 2u up to 3. Of course, the uv squared minus v isn't in this picture because that's telling me a number that every point on this thing produces. So there's a surface up here somewhere that is this. And so now, it's just like partial differentiation, only it's backwards. So in this one, the v is a variable and the u counts as a constant. So that's a v equals 3 on 2u and a v equals 3. So the u is a constant, so it'll still be there when I integrate. The v squared will go up to 1/3 of v cubed, and the integral of v is 1/2 of v squared. This is going to be awful, by the way, but there you go. And so I figure out what that is. So I sub in v equals 3. That's the v equals 3. I sub in v equals 3 on 2u. And I figure out what all of that is in terms of u. So what have we got? Yikes. That's 9u. That's 9 on 2. 27 on 8. 9 on 8. And that would be 9 on 8 again. And now it's just an ordinary integral just in terms of u, and I can do it now. So 9 on 2u squared minus 9 on 2u minus 9 on 8 times 1/5 of u to the 5 plus 9 on 8 times 1/3 of u cubed from 0 to 2. And then you'd sub in the 2 and the 0. Which is whatever the hell it is. Okay? Which is whatever the answer is. Okay, so I find that vertical line thing helps me to focus. You just pick any one of them. It might have been easier if I'd gone horizontally. I don't know. Okay? Vertical lines are easier to think about because you've got a function here. If your area had been on the underside, it would have been from 0 up to 3 on 2 on u. If your area had been this way, the formula would have been different, of course. So the hard bit is finding out what the formula for that line is and thinking, I have a point A and I want to know how far does it go. All right, and the final formula that we had was a surface in a vector field. That's what we need to do last. Actually, technically there is one more. There's a volume in a vector field too, which is a whole different story. So your surface in a vector field so this time there's a vector at every point, and you have your surface in there. And what you're going to do is just like with the curve in a vector field, what you're actually going to do is you're going to dot your vectors in your vector field with a vector that's based on the surface. So with the curve, we dotted the vector field with the tangent vector to the curve. Well, this time we're going to dot the vector field with the normal vector to my surface. So that's what we're going to do. And so in the end it comes out to the integral across the surface of vector s dot ds is the integral across my region of f dot normal vector du dv. Yep. And the normal vector is created in the same way as it was last time. Interestingly, it's a scalar triple product, so it's actually the determinant of a matrix. But again, my n, as it was before, was my x u cross x v. All right, and they are all the raw integrals, so like how to do them raw. And then there were rules for how you could turn one from the other. The volume integrals was a whole different story. I didn't get up to that. Did he explicitly show you how to do a volume integral? Or did he just mention it in one of the theorems? You're not sure? I reckon you just used the theorem to do it.
I'm pretty sure it's just the one where it's like is it and then you've got like the 3 different coordinates for it once you figure that out.
Alright. Just let me look it up.
I think he did one, and he also did one where he converted on a surface, but it was easier to do volume.
Right. Okay. Your volume integral is the same as a surface integral. There's just 3 directions to do it in before you. All right. So there is one final thing. There is a volume integral across a scalar field. And so what you end up with is some sort of wicked volume, and it's all coloured in on the inside. It's not just the surface of the object, it's on the inside of the object too. And that has a parameterization as well. Okay, so you can go from an x, y, z, or possibly an r, theta, phi, and integrate that. Yeah, it's the divergence theorem, but you can do it direct, right?
All right, flip back a couple.
Yeah, I've got it. Yeah.
But you said you didn't have enough.
Ah, well, I borrowed them. So, yeah, your dv, sorry. Can just be written as of like your f dx dy dz, something like that. And then there's this neat trick with a Jacobian where you can translate it into some other coordinate system and you'll get, it might be, you know, something like that. We did that in one of the assignments, didn't we? Yeah. So I did figure out this cool thing with the Jacobian, like at least for myself, of trying to remember how it worked. It's the matrix that has, it's the determinant of the matrix that has every vector, everything differentiated with everything else. So the concept is that your original function is written in terms of x and y and z. And they're all in terms of r, theta and phi. And your Jacobian, these derivatives, dx on dr, dx on d theta, dx on d phi, that's the first row of your Jacobian, and that's the second row of your Jacobian, and that's the third row of your Jacobian. So those derivatives become the rows of your Jacobian. That's how I just needed a way of remembering it. Apparently, if you're doing it in 2D and you're just switching to polar, it'll just be R. Yes. And we did spend quite a lot of time with people in the drop-in centre trying to figure out how the hell spherical coordinates worked. Because in the spherical coordinates, the R goes from the centre to the edge, and the theta goes from, one of them goes from 0 to 2 pi, and the other one only goes from 0 to pi, because you come down the surface of the sphere from the top to the bottom. So there was this idea that you can get a sphere in 3D, and at any particular, you can get, I don't know which one is which, but you can actually, it's right at the end, isn't it? No? Yeah, so the phi, your sphere is made up of a whole lot of circles like this, and what you do is that you do your circle down, your line down from the top, and at any particular height, you look at just this circle, like that, just that circle there, and you know that this is R, and so this must be, this radius here must be R sine phi, because of this triangle here, that triangle there, there's a phi here and there's an R there, and this radius here is this radius here, and it must be R sine phi because it's opposite the phi. And then the coordinates of a circle, if you go round this way as a theta, will be the new radius cos theta R sine theta. And so you know that that capital R is actually R sine phi. So we end up with R sine phi cos theta R sine phi sine theta, and then the height is R cos theta cos phi. Pretty sure. Yep. And that was the only way I could get it into my head of remembering it, is that you first pick your phi, even though it's at the end, even though you think of it as the last thing, you pick your phi first, and you rotate down from the top of the circle, and that gives you a slice, and that slice gives you the x and y coordinates. So your phi goes from 0 to pi, your theta goes from 0 to 2 pi, and your r goes from wherever it, from 0 to whatever the actual radius of the sphere is. So that took me a couple of days to figure out. So, yeah. All right. Well, yes. And so the idea is that if you're doing it in a dr d phi d theta d phi, you're going to have to do your Jacobian because it's all supposed to be in x, y, z to begin with. So, yeah. But you only need the absolute value of that, and it like comes out to like 3 sine theta or something like that, is what it came out in the assignment. I'm glossing over things, but it's partly because I don't know them, and partly because there's not enough time. Okay. Doing okay. So, that's all great. There was something that we're not up to yet, which is that there's all these awesome theorems that, well, there's 3 theorems that describe how volume integrals are connected to surface integrals and how surface integrals are connected to path integrals. And they all involve this operator grad, which your lecturer described as this. So, and someone came to the drop-in centre and they were asking me about this, and they said, "Oh, it's just this." No, you know what grad is? It's just this. And I said, "I don't know what grad is." Anyway, now I know. So the concept is that this symbol represents that. And it's designed to differentiate both scalar and vector fields. Okay, so there is the grad, there is the div, and there is the curl. And your grad is designed for scalar fields, and your div and curl are designed for vector fields. So grad was the scalar field f, and it went grad f and then you just bring the f inside each one of them. That's how the notation works. Lovely. And this is the same as the grad f that was back in Maths 1b, at the very end of Maths 1b, and it tells you 2 things. It can help you to find a directional derivative, and it can help you to find the normal vector to a surface. So if you have a level surface, it will tell you the direction of the normal vector. So you've got 2 things, so useful for. So we have that grad f is normal vector to the surface f is some constant. Any constant will do. So those normal vectors that I wrote over here, right at the beginning, that pink vector there, that's grad f at that point. Grad f will be different at every point, right? Because it's still got an x and a y and a z in it somewhere. But at every point, grad f will describe the direction of that pink vector. As long as that level surface has been produced because of a scalar field. And it's also grad f dot with some unit vector is the directional derivative in the direction of that. Of f in the direction of b hat. And the hat in this course appears to mean unit vector. So yeah, you have to use the b to be a unit vector. Technically in this sentence here you don't need b to be a unit vector, but in this calculation here you do need it to be a unit vector. So you can say in the direction of 1, 3, 5 if you wanted, but you have to convert to a unit vector to do the calculation. And not just that, it's also, if you figure this out, it's also the direction in which the scalar field is changing the quickest. So nope, just grad f equals direction is changing the fastest. Concept being that, I'll just shift that up. See how it's going from 5 to 6 to 7 as it goes out this way? That's saying that, look, you'll get the quickest change to a higher numbered surface if you head that way. But if I headed down this way, it would take me long. So if I was, say, here at 5, it would take me a long time to get to the surface that belongs to 6 if I went this way, but it would get quickest to the next surface if I went out that way. And that's the grad f. So it tells you which direction to go most quickly to get to the next level surface that's higher up. That has higher up in the sense of having a higher value for its function. So that's grad. Grad is awesome. It tells you all of those things about surfaces. And then there was div. Which was for vector fields. And div was the divergence, and it was delta dot f, like literally. So it's d on dx, d on dy, d on dz, dot, and f has 3 coordinates. It's got a function here and a function here and a function here. And so it will be df1 on dx, df2 on dy, df3 on dz. That's grad. That's div f. I have no clue what that means. But yeah. So, oh, sorry, pluses. It's not a vector, it's a number. So what the div does is it turns a vector field into a scalar field. Okay, so I've magically taken my vector field and done the del dot f, and it's become a scalar field because this thing here is just a number. They're just added together. Okay. Sorry, yes, it's this times this plus this times this times this plus this. It's a dot product. And curl, do note the grad turns a scalar field into a vector field, because we took a scalar, which was just f, and we turned it into a vector. So they do the opposite thing. And the curl, which was also for vector fields, is cross f. Cross product, which means you'll do this. and you'll get something wickedly strange when you do that. So you'll go all those little determinants. All right, and then this is a vector again, because it will have in its coordinates df3 on dy minus df2 on dz. And then the next one will be minus df3 on dx plus df1 on dz. And the next one will be df2 on dx minus df1 on dy. But I can never remember that, I just do that. Okay, so this is now a vector, right? So this takes a vector field and produces a brand new vector field which points in some other direction. And the reason we define these, as far as I can tell, I'm sure they tell me something really important, because there's all these things about being irrotational and conservative and whatever. A conservative vector field is one where this number always comes out to be 0, and an irrotational one is where this always comes out to be the 0 vector, and something like that. And that's really important in physics, apparently. And what we need them for is to define these fabulous integral theorems that relate volume integrals to surface integrals and surface integrals to path integrals. Okay, and that's where the last bit that I got up to when I was doing my study last night came to, that there are 3 theorems, and it was really, I must say, extremely difficult to tell at what point he was mentioning the actual statement of the actual theorem in the notes. Like, there was one of them that he put a box around, but the rest of them, it was in the title, but there were several pages that said Stokes theorem, and I couldn't tell which one it is, but I think I figured it out. So based on his examples, divergence that is that. Which is the same as, so this is a volume integral. So this is the divergence of a vector field, which is a scalar field in its own right. So this is a scalar here. So we know how to do integrals of scalars. And this is also a scalar field, technically. But if you think about it, this is the definition of a vector field integrated across a surface. So, and that circle there is implying that the surface is closed. It's like the surface of a ball, and the volume is the inside of the ball. Okay? And this is the same as because we were told that that's how to do a surface integral. And this one over here is the same as like a dx dy dz thing, okay? But that's the actual theorem there. So basically what it says is that it might be sometimes easier to find the actual vector field across the surface, or it might be easier to find the volume of its divergence inside inside the surface in the volume, and they'll come out to the same answer numerically. Even though technically this one is in units to the 4 and this one's in units cubed, they'll have the same answer numerically. And then there's Stokes. which was that, which is a surface integral of the curl and that's a path integral. And so in this one, the surface, there's a path, and then your surface lives sort of around the path. Okay, the edge of the surface is your path. So this is the C here, and this is the S here. Up here with the volume, you have sort of a wire frame. That's the surface, and then the inside of it, that's the volume on the inside. So note that this is not actually a closed surface. It has a hole at the bottom, and the edge of the hole is the C. And we've got methods of calculating these things. Remember that this is going to be, this one here is actually going to be that, according to what we calculated before, where the n is xu cross xv. And this one here is like your a to b of f dot x dash dt. That's what that one is. Just going back to the definitions of what those things were in the old ones. And then the third theorem was Green's theorem. I haven't put them in the order they were presented. Which took me ages to figure out what the hell it even was, and I'm still not 100% sure. But what I have is that I have a function that is, yep, rightio. I would love to do it in terms of a function, but that's not how it's written in your notes. Your notes, it's written like this: U and V, capital U and capital V, continuous functions on a region defined in terms of x and y. And so we get that the integral comes out to this. And what does that even mean? Well, apparently it means this. So it'll be the integral from like a to b of whatever you parameterize the edge of the thing as. So this one is actually designed specifically for things that are flat, that are inside a zone. So you have, this is your boundary of R, and this is R in here. And you'll notice that technically that capital U, capital V is really just a vector function. It's just that we're all in 2D now, and this should work just as well in 3D. So this is really the same as Stokes's theorem, but it's all in 2D. So, yes. All right. Yeah, that was fun. So, do you want to talk about anything else to do with that, or me do an example or whatever? What do you want me to do now? because I should probably get back to the drop-in centre soon, being the last day before the assignment, though I've kept you all out of the drop-in centre. That's what I could find on that in the notes. So it's still not in any particular nice order, but I do quite like writing the div, not the div. Where's the rest of my theorems?
What do you mean by neomorphic function?
That's a really good question. Let's look that up. So that's the vector calculus. I don't know if that helped, but it certainly helped me to look through all the notes and put it all in one place. So my question that someone asked was, based on this, just give me a second. This flowchart that Barry gave out, which talks about how to do contour integration, and the first step of the flowchart says, is it a meromorphic function? I'm going, what does meromorphic mean? Let's look it up, hey? Okay, so we've ooh. We have passed out of multivariable calculus and passed into complex calculus. So let's just see what it says. I think meromorphic has multiple meanings. Ben.
Turns out the complex nodes were even hard to find.
So someone sent me the complex notes, and I put them all into one big, like the notes, and I put them all into one big file. So blah, blah, oh. So a function is analytic, regular, or holomorphic. Maybe I should just search for it. Aha! A function whose only singularities in the finite complex plane are poles is called meromorphic. That's just obvious now, right? Yay. Well, apparently it's to do with these Laurent series. So if your Laurent series has infinitely many negative powered terms, then that's called an essential singularity, and it's basically saying if your function doesn't have any essential singularities, it's meromorphic. But I don't think you do non-meromorphic functions in Engmaths 2B, because it did say on the interesting. Not really sure what you're supposed to do with that. Anyway, that's what meromorphic means. It means that it doesn't have any essential singularities, meaning ones that where the Laurent series goes on forever, where the negative bit goes on forever. So there you go. Complex calculus, I found, is kind of that slightly bit more bizarre than ordinary calculus. even the vector calculus, because the difference between it is that at every point, well, this is the picture that's in my head. I like to have pictures. This is your Argand diagram, which will put a complex number as a point in a plane. And so this would be the point, x plus yi. Okay? So the whole purpose of complex numbers was to turn points into numbers in their own right. So rather than treating the points as vectors, which is what you do in vector calculus, you say that every point in that plane is a number in its own right. It counts as a number. You don't have to treat the two separate coordinates separately. If you don't want to, you can say it's just a number of its own. So for example, this point here, which as a vector would be the point 1, 0, as a complex number is the number I. Okay? When they first invented complex numbers, nobody thought they were real, because they aren't, and they didn't like the concept. And they actually tried to do this in 3D and they couldn't. And they had to use 4 dimensions to do it, and when they invented the quaternions, which is the 4-dimensional version of complex numbers, that is why we have the dot product and the cross product. So the dot product and the cross product came from trying to do this complex number thing in 3D. So that's why we now have them. Yep?
If they don't exist, why do we have them?
Oh, well, they do exist in the same sense that anything you can imagine exists in somehow. Like look, there it is. The number I is right there. It really exists. Well, they're just ways of representing things, right? The points on a plane certainly exist, and I can represent them with complex numbers. So complex numbers do exist in that sense. They're useful because a lot of the integral stuff that was actually really quite complicated in vector calculus is still fairly complicated, but not as complicated in complex calculus. Okay? So that is why we have them. Okay. And also just because, mathematicians go, oh, wow, look at that. We can create this whole new family of numbers which does all this cool stuff. Okay? But it also happens to be useful. It also happens to be useful. Okay. So what we're going to do is we're going to do the same thing that we did in multivariable calculus with the path integrals, and we're going to do it in complex numbers. And so we're thinking that, look, when we try to do an integral in real numbers, you had your x's, and then every x, you could plug it into a formula and it would give you a number. Okay? So it used to be with real numbers, what would happen is that you've got this function, and at every point on this line, there was a number. And what you would do is you would imagine those numbers as being a height of some sort. And then you would add up this area, and that would be the integral. Okay, but you're very, very used to thinking of functions as an x-coordinate and a y-coordinate, but what they really are, at least in this sense, is a line with numbers attached to every point on the line. So there's the number which tells you what x is, and there's also the number that tells you what the result of the function is. Okay? So that's your real integral. And we want to do something very similar to that with a complex integral, except that in complex numbers, instead of having xy, instead of having x, we have an x and a y, and every point here has a number associated with it. Okay? So there's the complex number that tells you where the point is, that's your x, and there's the new complex numbers which tells you the result that comes from that point. Okay? And so all of these options here are complex numbers, and we could, if they were real numbers, we could represent them all with heights and do a surface, right? Do some sort of volume. But it's worse than that, because those numbers there might be complex numbers. So it's almost as if at every one of these points, if we zoom in on it with our lovely little magnifying glass, here we are at that point, and it's almost like at that point there's a little complex number diagram that tells you what the result of the function is. And at every point there's another one of those. At every point, there is a complex number that lives at that point. So what we're almost doing is we're really making a vector field. So, because we can imagine that complex number as an arrow. So you can put your complex numbers as points, and you can almost think of these as arrows at every point here. So it's like doing a vector field in 2D. Right. So what we used to do with integrals in real numbers is we used to do like the integral from a to b of like f dx. And that was great, because what we'd do is we'd just find an antiderivative and we'd sub in b and we'd sub in a and we'd subtract and it would give us the answer, which was lovely. But if you have an a and a b somewhere in complex numbers, there's any number of ways to get from here to here. Right? So we have to start thinking about doing them across paths. And if we stretch out that path, so what I'm going to do is I'm going to pull that path out and just draw it along here. And at every point on that path, the result is not actually a real number like it was back here. The result is a complex number. So it's almost as if at every point on that path there's a little complex plane, and the answer for this one is here, and there's another little complex plane here, and the answer for this one is here, and there's another little complex plane here, and the answer for this one is here. And instead of this height being just a height, it's a height pointing in all these different directions, over here and then over here and over here. And you want to add up all of those complex numbers and produce something, which is a complex number. So, but the nice thing about it is that complex numbers are sufficiently nice for it to work almost all the time as if it really was real numbers. So you have this awesome thing that if there's no wickedly stupid bits in your function, then you'll get the same answer no matter which path you took. Okay? So that's where this thing here on the computer screen is saying that you got meromorphic function, is the contour open or closed? Is it open, which means that it goes from one point to another and not back to where it started? And therefore, is it simply connected? And if it is, then it doesn't matter. You can just, doesn't matter which path you pick, it'll always be the same. Whereas if it's a closed path, then you can do the fabulous thing with the residues, and you'll always get the same answer there too. So that's the flow chart. So there was, you need to fill in the details on that flow chart to help you figure out what to do at any of those points. But we do have some nice functions. We can go the integral of e to the z from I to 3 minus I. Well, let's look at our flow chart, hey? Meromorphic function doesn't have any singularities at all, right? Meromorphic meant that the singularities were, that it didn't have any essential singularities, and this doesn't have any at all because it's e to the z. Is the contour open or closed? Okay, so it's open because it just goes from one point to one other point. It doesn't come back to where it started. Okay, and is it simply connected? I presume, I don't know what that means. We'll have to look that up. But I presume it is simply connected. Not sure. I think it's to do with the fact that your function doesn't have any weird bits. I think it might just be to do with the fact that your path doesn't have any gaps in it.
Yeah, or it doesn't have that one split up into multiple segments.
Yeah. So if your path doesn't have any gaps or jumps or turns on itself, which it doesn't because I can make a straight line, therefore it says I can just do this. The integral of e to the z is e to the z. And I'll just do exactly what I would do with real numbers. So the concept of the picture of my path is this. Here we are at I, and here we are at 3 minus I, and I'm going to go from there to there. But technically any path that goes from one to the other would give me the same answer. And I'm just going to leave it like that because that's awful, right? You can convert to sines and coses. If I was being particularly nice, I should have put some pi's in it, but there you go. And sine and cos are meromorphic, and so is shine and cosh. ln is as long as you don't go across the x-axis on the left-hand side. And most of them you can do that. And the other thing that happens is that if you've got sees that curve, then the residue theorem tells you that you can try and figure out the Laurent series and find the n minus 1 power term. So you should be able to just, what do we do? The first derivative, we don't differentiate it at all for a simple pole, don't we? So the idea is that this function has a pole at I because e to the z is fine, and the z minus 1 isn't defined when z is I. Z minus I isn't defined when z is I. And then I'm just going to have to look that one up. So it would be the 0th derivative. So it'll just be e to the I, right? So the residue of my function as z goes to I is going to be 1 over 0 factorial, the limit as z goes to I of the 0th derivative of my original function of z minus I to the 1 times the 0th derivative of my original function evaluated at z. That's the formula. I know that there's one for a single one, but I don't know it well enough. So basically that's saying that it should be just the top of my function evaluated at I, right? So that's which is e to the I. And so therefore the integral of c of e to the z over z minus I dz is e to the I times 2 pi I, right? That's the residue theorem. Ta-da! So the key is if you've got multiple things on the bottom, then you're going to have to deal with each of them separately. And it won't be the top of the function, it'll be the entire function, everything except the bit that involves your pole. But it doesn't matter if it has poles outside your curve, only matters on the inside. That's my understanding of it, and I think that there's not all that much else to it in an exam. I could be wrong though. Well, I reckon it's time for me to stop. If you do have questions, we can give it a go today. It's on for young and old on the last day before the exam. And You feel free to use the phone in the Maths Learning Centre to call Barry and ask him questions directly. I'll see you guys around. Good luck with your exam, hey?